Boolah.
All right.
Oops, excuse me. That's all good. That's all good. My bad. You were leaning before I started walking.
Oh. I'm gonna do. I want to talk about some things today that'll make this that we haven't quite talked about.
Why is there so much?
It's 2 pages. It's really
It's
not
not
that
front
much.
and
It's not. Yeah, it was not front and back, which it was supposed to be, but apparently the printer barfed. So
For some reason, the printer doesn't like doing front and back.
this is our
Pretty
home
good.
print.
Oh, then.
I don't know why I'm doing that. We'll get some stragglers, maybe.
Yeah.
So, let's take a look at this really quick, and then I want to talk about basically what you'll need to do the entire exam. We haven't quite talked about it.
Oh, there's 2 pages.
Yeah, there's 2 pages. Make sure you have 2 pages. There are. So let's go through this. So, take home, do the Friday, end of the day of finals week. However, I will only be available, I will not be answering questions on Thursday and Friday of that week. We can talk anytime, we can set stuff up, you know, all before that. But if you are a person who is occasionally late with things, you know who you are. There's a bunch of you.
I couldn't tell if you were looking at me or not.
I'm not looking at you. I'm looking at the camera
I mean, I was
to
looking at
address
the
the whoever I might be addressing. If you like to turn stuff in late, you will be on your own for those last couple of days. So start early. We'll start working on this hopefully a bit today. So let's just go through it. The first problem, I've got a function there. That is e to the 1 over z. If there's any questions, that function is z to the 6th, e to the, and the entire exponent is 1 over z, so that you can get some Laurent action going on. And I don't know what Levine is doing. Something very interesting. Is that for Sydney or something?
No.
Well,
She likes doing the thing on her iPad.
cool. Oh, cool. That's neat. That's neat. Yeah, and a live version of this actually went up on our class page at 11. So, number 1 is pretty self-explanatory, at least parts A through C. Parts D and E, we need to talk about today. Problem 2, we need to talk about that today. Problems 2C on the next page. D, everything else we need to talk about. But you have the essential skills. It's really just this Cauchy residue theorem that we need to talk about that will make those doable. And a few tricks of the trade that we need to talk about.
Why aren't these printed double-sided?
Well, I don't know, Noah. Maybe it had something to do with that comment I had at the beginning that the printer barfed.
Oh, I didn't hear that.
Okay.
My bad.
Yeah, that's terrible. Unbelievable. This time it is your fault,
Yeah,
honey.
no. I was thinking about it.
It's all good. It's all good. So, if you just came in late, due next Friday, end of the day, the latest. I am only available for consultation up through Wednesday of next week. I will not answer questions about the exam after that. All right, so let's get going so that we can crank on this exam. Quick review. So this is all about residues, primarily the Cauchy residue theorem, but we want to talk about just a quick review of what is a residue. Since it's been a long time since we've been together, it's been nice. It was a great break. I hope you all got refreshed and had some goodness. Oh, and on Wednesday we will not meet. I'll just be in my office during this time. This coming Wednesday, yeah. So we won't have an official meeting. Come work in the math office area. I'll be there for consultation in my office, just for you all. Cool, so residues. If we take a function, f of z, and we crank out a Laurent series, that looks this. And this one, so notice this series is around, it's centered at Z naught. Ooh, blah, 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 keeps on cruising. The residue of F at the center of the series is this coefficient. So we say residue of F at Z naught, that's a semicolon there, not an I. It would be easy to confuse it for an I, is just that number right there. Quick methods for finding them. So let me see, let me get my little notes out. How do I find a residue? Because that's going to be where all the work really gets done in this exam. So, how to find? Step one is determine the order of the pole. And what I mean by that is how deep into the negative coefficients do we go? If it stops right here, that's called a simple pole. If it stopped there, that's a pole of order 2. So we need to know something about the type of pole, the depth of the pole. Step 2, let's just call it M. Let's say it's M. Get the residue. And we've got a couple of ways to do this. So if it's a simple pole, I wrote a little algorithm here. If it's a simple pole, in other words, M equals 1, the residue of F at Z naught is equal to limit as Z goes to Z naught, Z minus Z naught times the function. So you literally multiply through by this, times the, take this times the original function, and then in the end you can probably just plug in Z naught, but just in case, we'll put that limit there. Notice what multiplying through by that coefficient would do, or this term would do. It basically kills off this denominator and just leaves you with this, and then you've got an extra Z minus Z naught everywhere here. When you plug in Z naught for Z, kills all this, gives you that coefficient. So that's one way, or if F looks like this, it's clearly a ratio of two things, and it won't always be, but sometimes it will be. If F looks like this, and Z naught is a simple pole, then that means H of Z naught must be 0, and that's a 0 of order 1. And the top is not 0 at the point of interest. Then the residue of F at Z naught is equal to G at Z naught. So just plug it into the top, but take the derivative at the bottom and then plug it in. This follows from that thing over there. Easy. So simple pole, cake to get that residue out. If we have a deeper pole of order 2 or more, then it's a little bit more work, but still not too bad. So if a pole of order greater than 1, then the residue of F at that point is going to be 1 over the order of the pole minus 1 factorial. So again, remember, pole of order M. So here I'm saying M is greater than 1. Be a little more mathy. And we take then limit as Z goes to the pole. The n minus first derivative of Z minus Z naught to the M times the F of Z. So let's look at this and remember what this means. This means I've determined I've got a pole of order 3. So I multiply the function times z minus z naught to the third. And then take this derivative 2 levels, 1 level less than the depth of the pole. So if I have a pole of order 3, this will be a 3, and this should say m, excuse me. And the derivative would be the second derivative. Notice how up there, don't worry about that. Yeah, let's just keep this. All right, so that's it. That's all you need to get all the poles you need, except for one kind. If it is an essential singularity, if Z naught is an essential singularity, what does that mean?
Doesn't it just not stop?
Yeah, the M is not a finite number.
M is not a finite number. This never terminates. So it just keeps on cruising that way. That's an essential singularity. Then you want to get the series expansion, so get the Laurent expansion. And grab the coefficient from that. So that's actually probably the most work you'll have to do. Sometimes these derivatives get a little, there's work to do there, but it's just derivatives. And then just grab that coefficient. So let's do some why do I care about this? I think someone asked this last week. I can't quite remember. Why? Was that you? Was that you, Noah?
If it was an annoying question, it was probably me.
It was not an annoying, it's a great question. It's the question all math professors dread. What is this good for? Oh shit, now I've got to come up with something. It's good for other math, was the answer. So, one of the things we're going to use this for, the prime thing this semester, is the Cauchy residue theorem. There's a nice complete proof of this in our book. You can read that. I'm going to give you a heuristic, intuitive proof that I think you'll feel good about. I feel good about it. So Cauchy residue theorem. Let's get all the hypotheses up. We have D is a simply connected domain. I want to go review what that means. Good news is all your domains will be simply connected, so you don't have to worry about that. C is a simple closed curve in D if F is analytic on and within C. So if F is analytic on an open neighborhood containing C, I'm going to write that here, on and inside C. So here, let's draw a picture. This might be a little, so here I've got D like so. I've got a curve C that goes like this. I'm going to say it's positively oriented. Simple, it's closed. If F is analytic on and inside C, so what I mean is F is analytic on the curve and then inside as well. So F is analytic on an entire open set just containing that curve. That's what I mean by this. Except at a finite number of points. So except at points Z1 through Zn. So we've got these holes in here. Z1, Z2. And those are places where we're dividing by 0, or we have a Laurent expansion with a principal part, the negative stuff, at points. Then the integral, here's the money shot. The integral around that curve of f of z is 2 pi I, that's not a shock, times the sum of all the residues. Let's not use I, that's a little, let's use a k, to n. It's the sum of f at each of the residues inside the curve. little note here, only over the z's, zk inside the curve. That's all I care about. Now, why would this be true? So why would the integral care about the singularities? And all we have to do is come back to a result we saw a billion years ago. It all hinges on this thing. We proved this in class. You proved a lighter version of it. But recall this, that the integral around a circle at z naught of radius r, just gonna close the circle there, of 1 over z, well, actually here, let's just put it a little differently. Z minus z naught to the nth power dz is equal to a bunch of stuff. First off, what if n is a positive number? N is like 1 or more.
0.
Absolutely. Why is that, Noah?
Because if it was physics, I would say it is a conservative force, meaning that there is a definite antiderivative everywhere. And so no matter what path you take to get from one point to another, you get the same thing. And therefore, when you go in a loop, you just end up with the same thing.
That all sounds pretty good. I like that. The complex analysis answer would be, it's an entire function. And remember, we only accrue value at non-analytic points. So I like Noah's answer. That's got a lot of good physics love in it. But it's going to equal 0 if n is equal to 1, 2, that. But also if n is equal to -2, -3, -4, and you can prove that for yourself, it only picks up a value of 2 pi I if n is -1. That's the only time this integral has a non-zero value. So now, think about this series. I've got this integral, and maybe it looks, so it looks like this. And then I get out the Laurent series of f, so I'm going to just plug in for this series, dot, dot, dot. This is super abusive mathematics. I'm being very loose. It's casual mathematics. I'm not being very careful about pulling the sum inside here. And then doing what I'm about to do. dz. So you want to do that integral? Look what happens. All this stuff, the integral of that is 0 because of this result. The integral of the term before it is 0. The integral of that, that's just a constant. That's going to go to 0, 0, zeros down the line. The only thing that matters is this. And so it's integral of a to the -1 over z minus z naught dz. And this is the residue. So this is, pull that a naught out for a sub -1 out front. That's the residue of f at z naught times this integral. And that integral is 2 pi I. So this equals the residue of f at z naught times 2 pi I. And this is a simple version where there's only one of those singularities inside there. But we just do this expansion at each of those singularities, and the integral will be the sum of all these various residues times 2 pi I. So that's why there's a dividing by, well, no, I just proved it anyway. Great, solid. Good. So just a rough feel for why this is so. We don't need this to do it, but it sure don't hurt to have it. So let's take a look at, I've got a series of integrals here for us to crank out. So first integral is this. So let's find the value of integral z plus 1 over z squared z minus 2i dz. And the way this works is there's a bunch of different places where we want to find this integral. So the first one, let's say here, A is where C is, I put a C here, so C and here, C will just be the unit circle centered at the origin. Okay, so now we've got our problem. We know that what we need to do is figure out residues. And so step one is draw a little picture of the curve. So there's I, there's 1, minus I, minus 1. So there's C. And look at the function, look at the integrand and see where it has troubles. Where's this one have troubles? 2i, and where else? And 0. So one of those troubles is right in the middle of this. And the other trouble is not inside there. So right now I only need to worry about the residue at 0. And I'm good to go. So in other words, this is going to equal 2 pi I times the residue of this function, z plus 1 over z squared z minus 2i at 0. That's it. Worst comes to worst. Look, friends, worst comes to worst. It's Friday at 11 and you haven't started this exam. God help you. But so let's say you can go through and write this for partial credit. You haven't done the hard part, but you got something. You know how you're supposed to do it if you had the time that you should have given yourself. So we need to figure this out. All right, what is the order of 0 here? It's a pole of order what? 2. Just use your lip. And c squared. It's 2 zeros. So this is a pole of order 2. So we have a pole of order 2, and there are results that we've talked about. I know that, look, 0 is a 0 of multiplicity 2 for the denominator. That means it's a pole, and the top isn't 0 at 0. So that means it's a pole of order 2. It's just that simple. Pole of order 2 at 0. So to get the residue, I'm going to use that derivative result. So what I do is I multiply through here. I'm going to do limit as z goes to 0. I'm going to do the derivative, just the first derivative. This is a pole of order 2, so I need a first level derivative. I multiply by z squared, and then I've got the rest of the function. And I'm writing this all out, but you can see the niceness that's going to happen, right? Like, yeah, lovely. So all we have to do is basically cancel out that part, take a derivative, plug in 0 for z, and we've got this. So this is going to be lim as z goes to 0. Derivative of this thing, I need the quotient rule. So using the quotient rule, it's the derivative of the top times the bottom left alone, minus top left alone, times the derivative of the bottom, all over the bottom squared. Why simplify? We don't need to. We can just plug in 0. So we're going to get negative 2i minus 1 over negative 2i squared. And then we're going to take that to a plus bi form because that's the kind of people we are. We do that on all our answers because it makes me warm and cozy inside. So let's see, what do we got? We got negative 1 minus 2i. I'm headed toward a plus bi form. This bottom thing is negative 4. And so I've got 1/4 plus 1/2 I. That's my residue. And now I have my answer. So my final answer is going to be 2 pi I times that beast. And I simplify. And notice that we're going to flip here, so I'm going to get pi, negative pi plus pi over 2i. And that's my answer. We stop for a second, because I'm just ripping. You get to do the next one.
Where did you get them made? Oh, because, never mind.
Yep, are we all good?
Yeah.
Cool. Thanks for keeping an eye on me, though. It's been a good break. I might have forgot how to do stuff. Basically, I spent most of the break learning for the class I have to teach next semester. I now understand modern geometry, just so you know, when we get in there, I know what the hell's happening. I got it. It's awesome. My complex analysis friends who will be in there, you're gonna have this tiny little edge, but I'm gonna show you so much stuff we didn't talk about at all. It's gonna be cool. Gonna learn a lot of stuff about Mobius transformations. That's really at the heart of it, which was shocking and wonderful. Any other questions on this? Because it's your turn. Where do you think the next curve, you know, you've been in school long enough, where's the next curve gonna be centered?
2i.
2i. So let's say z minus 2i. And I wanna keep this one from hitting the 0 as well. So I'm gonna set a radius of 1 to keep out the 0. Right? So you always sketch these out. We've got 1, 2i. And then we've got a radius 1 curve, so there's our C. There's only one of the singularities in there. So we have a pole of order 1 at 2i. Do the integral for me, please. So now please find this integral. Same function. Use the residue theorem. Dankeschön. Also, for the folks who came in late, we're not meeting officially on Wednesday. I'm gonna be in my office chilling for consultations on this exam. This sounds nice, sounds relaxing. Yeah, I think I recorded, I gotta keep this one word second, Nathan, just because I think I recorded the wrong place. Thank you. Yeah. This then? Awesome, thank you. And then 6 and 7.
Yes, I was gonna.
Okay. Wait.
Oh yeah, 6163.
Yes, sir. Yeah, they're actually pretty chill. They're not. They're some of the less oppressive assignments I've given this semester.
Actually, I think it's only 62, I think, or 61.
Oh, you think you might have it in there?
I have it in here. I thought I had one question for that one, but I'm not sure. Where is it? Yeah.
You got it. Cool, cool, good, good. Good to hear. So we have a simple poll, and you can use any of those first methods that we talked about. Kind of feel like the first one's the easiest. I mean, that's just cake. Right, that other squared came from the derivative, yeah. That's interesting, 2 pi I. You already did the limit, what am I talking about? Plus 2i over -4, and what do we get? I gotta be careful, because it's easy to screw this up. I think we're gonna get a negative pi over 2i, and then for the real stuff, we're gonna get negative pi. I think. Let me know, did I do that computation right? Let's see. Maybe. Yep, it would be, thank you. It's cool, the one has pi, the other one, why doesn't the, oh, it does, they both have pi, what am I talking about? Wacky. So I have one last question, and we've actually done all the work for it. What if, and I'll answer any questions you have over all this, but what if I have z equal to 3 centered at 0? So what if that's my curve? What are my trouble spots? Well, I come here and I look at the trouble spots. There's that one, there's that one, and now I got this curve that's got them both inside. Cauchy residue theorem says add up the results that you get for each of them. That's it. So here, the integral over this c, our function, is going to be 2 pi I times the sum of the residue at 0. I'm going to abuse notion here, and then the residue at 2i. But that's this answer, that's just the sum of these two answers, because we've already multiplied each of these by 2 pi I, so this equals sum of previous two. And when we add those together, what do we get? 0. Not because that thing's analytic, but because what happens at the poles cancels out. This is basically problem 1 on the exam. It's a lot like this. It's very, very cautious, slow entry into the waters. Can I answer any questions about this? I want to do a real integral application next, which is where the fun starts. There is a cool bonus problem on there that I need to give you tips for. Maybe I'll have time today to do so. So take a look, let me know if there's any questions while I gather my senses. Yes, ma'am.
So here we have two trouble spots technically. If we had 3 and our final curve had all 3, would we just add all 3 up?
Yep. That's correct.
So to find those 3, we would just make imaginary circles around it and just work with those.
Well, not imaginary circles,
Right,
but
circles.
yes. I guess they are, because everything we do in here is imaginary, but yeah, so I like that. Yes, ma'am, that is correct. Yeah. Other questions?
Can you restate why, when n is a negative number, but not -1, the integral from 1 over z minus z naught to the n?
Sure.
Yeah, is 0, because I don't remember that.
Yes, so for
Just 'cause
this
it's
one,
like analytic?
it's not analytic, it just turns out to be 0 in the kind of the way that that does.
Yeah.
So when we had this, and and this is a positive number, you're cool with that being 0, right?
Yes.
That's, okay, awesome. Then we took a look at this, this was a homework problem, where we had, this was a homework problem at some point, and to find it, you had to parameterize.
Okay.
So you replaced, oh, and this should have been in Z naught. But our parameterization of C is going to be Z naught plus e to the I t. T runs from 0 to 2 pi. That all sound good? Yeah?
Yeah.
And then when I come in here and do my parameterization, so this is my r of t, or gamma of t. This is going to become integral over the parameter range, 1 over, replace z with this thing. Notice the z naughts will cancel, and that'll be just this beauty. And then our prime of t is going to be I, e to the it, because this goes away.
Okay.
And you see that? So then I got this.
Yeah, okay. So I see how it's 2i.
Cool. And so, yeah, so that'll be 2 pi I when we get,
Okay.
right, because so this is just going to be
Yeah.
an I 0 to 2 pi dt.
Yeah.
So you get, yeah.
Okay, so what if it's,
Yep.
but like what if it's negative?
Cool.
What if the exponent is a 2?
I like it.
Z minus
Let's
Z
do
naught,
it.
Or just,
You got it.
'cause
So
that's-
let's say we got this, and we're going to say m is bigger than 1. DZ. I'm going to use the same parameterization again. So I'm going to use same curve. Let's just use that parameterization. So what we'll get is really similar. We've done so much of the work. It's going to be integral 0 to 2 pi. Now instead of e to the it, I have e to the im t in the bottom. I just raised that bottom. And I still have the same differential change over here.
Mhm.
So now, now there's some simplification that needs to happen. So this is integrals, pull the I out front, integral 0 to 2 pi, e to the I times 1 minus m t dt. Does that look okay?
Yes.
Cool. So since m is an integer bigger than 1, this is a negative integer bigger than 0. So this thing here, since m, let me just write this out, let's let everybody see this. So since m is equal to -2, -3, or something like this, oh, this is going to be a positive number, right? So 1 minus m will equal
No, m is. Shouldn't the total be negative at the end?
well, since m is, oh, right, because m is positive, right, thank you. Yeah, thanks, Noah, yeah. So, so m is 2, 3, 4 on up, so this will be what? -1, -2. This exponent is one of those numbers, right there.
Yeah.
Sound okay? All right, cool. So now I do some calculus, so I take the antiderivative of this. Basically, what's going to come out in front is going to be I 1 minus m. And I already had this I out in front. And then I've got e to the I 1 minus m t. And that goes from 0 to 2 pi. Let me know if that sounds okay.
Okay, and then since it goes from 0 to 2 pi and it's e to the I, then you just go from the starting point of the circle.
That's right.
Okay.
That's right.
Yep.
Yep. And you're just spinning around the circle at different rates and, reverse spinning, but you still just do full revolutions. So you get 0.
Okay. Cool. That
Yeah.
makes sense.
Awesome. Cool. Thanks for caring. Makes me happy. Thank you. All right, let me do maybe 2 more examples. What if I want to do something fun? Like, let's see. Let me take a look at the exam and see if I want to do different examples now that I'm thinking this through. Yeah, okay, sure.
That's not food.
good?
Don't yell at Labina because Labina hasn't eaten.
Again?
And that's not
Milk's
food.
not
Milk is
food.
not food.
What?
Well, I think the Dairy Council might disagree.
That's not
Milk
a
is food.
substantial meal.
It's not
Let me
good
rephrase.
food.
I have
Weird
sandwich
food.
in my bag.
You need to plan your meals.
It's better than no food.
Exactly.
It's not no food.
A glass of milk is better than maybe a glass of water. There might be some substance to a glass of milk, but I'm still upset at the situation because that's not a meal. It's not breakfast. How do we
No.
start our day off with a glass of
Take
milk?
her out for lunch after class.
I have extra meal money.
Oh my god,
Yeah,
there's
we
so
do.
much.
Very willing to swap.
Cool, awesome.
Math.
Yay.
Alrighty, good lord. What if I have this integral here? So, let's see, I gotta change it so it's not your exam. Maybe it's even a little harder than your exam, kind of, yeah, more or less. Let's say I wanted to do this. This cannot be done without a formula table in Calc 2, which is where you would do this. No matter how hard you try, U substitution, maybe a trig substitution would work on this, but God, they're horrible. My God, if you ever had to do a trig substitution, which I hope you did, I think we stopped doing it at some point because it was just too horrible and emotionally scarring for people or something. But if you had to do a trig substitution on this, you would say, I'm gonna let x be the tangent of theta, and then d, oh my God. Because tangent squared plus 1 is secant squared, and then you've got a secant to the 6th in the bottom, and you hope to hell all this works out. But it's usually very painful.
Probably cried.
But then wouldn't you have to account for the facts?
Come again, please?
Then isn't that just a U substitution though? But so you have to divide by something somewhere?
Yeah, but it ain't pretty. You'll end up with a trig integral. I mean, let's see what you would end up with. Let me prove this to you. That this
Trig
is
integral is
truly horrible. Derivative of tangent secant squared theta, not d theta. So I'm gonna do my changes here. I also have to change the range on this. Usually you wouldn't even get this here. But think about the fact that tangent is negative infinity when we have negative pi over 2, and it's positive infinity at positive pi over 2. I'm just thinking of a tangent curve that looks like this. That's pi over 2. That's tangent. So I can change the limits in this way. The top would become secant squared theta d theta, and then the bottom would become tangent squared theta plus 1 cubed d, and I did the d theta change. So this becomes secant cubed, or secant squared inside there. This whole thing simplifies to a 1 over secant to the 4th, which is a cosine to the 4th. And then you have to use half angle to break that down into other things. What's that, Lavina? Did you say what the hell? I think you did.
He said that's not bad.
That's not, it isn't bad.
Not as bad as I was thinking.
It could be worse.
Yes, exactly.
It could be worse. Yeah, it was actually not as bad as I was thinking either, but it's still not pleasant. Now you gotta get the cosine squared, diminish the degrees, and oh man. You'll have to do that twice. Without a table, that's painful. So what we're gonna do is use complex analysis. Now, last time I gave a complex analysis final, one person in the class just looked up formulas in a calc book. You will get no credit for looking up. Like this, we want to use, if you are not using complex analysis in every problem on here, you're actually not doing the problems. So please use complex analysis. Don't go look up the table for that. Don't use trig substitution. Don't do any of that. Here's what I'd like you to do. So, what we're gonna do first is consider a different integral. go from minus r to r, and notice this is the complex plane. This is the real axis, and that's the part we're interested in, what's happening here. And let's say this, so this is negative r to r, and then this thing up here, c sub r, is just the upper half of a circle of radius r. So our whole curve, gamma, is the union of these two things. And I'm going to actually find the complex integral of this thing, not over just this interval, but over that whole curve. So we will find the following. Integral over gamma, let's call it gamma sub r, because it does depend on r, of replace x with z's. We will find this, and we will show that this thing here goes to 0, that the actual value of this integral dies out as r goes to infinity. Whoop. Not 8. So that top part, the value of the integral on that top curve will diminish to 0 as we let r go bigger. If we let r go to infinity, this becomes negative infinity to infinity. It extends across the whole real line.
Sorry, that's a T.
Yes?
Why do you have two DZs?
That's a good question. Thank you. I shouldn't. Thanks for caring and noticing. Appreciate it. We will show this so that this integral from minus infinity to infinity of dx over x squared plus 1 cubed is equal to the limit as r goes to infinity of this integral. So we're going to find this integral as r becomes as big as we can, as big as we care about, really. And then we're going to let r go to infinity. And whatever value we get out of here, it will be this value because that top part will die away. The value on the curve, on the circle, goes to 0, and all you're left with is the value on the real axis. So this right here just means x is a real variable. So you could think of this thing right here as just that's integral restricted to the real line. That's our plan. So,
But
yes,
CR is only half a circle, so we can't use our nice loop formula.
we can, and we don't care about nice loops. We just care about complete closed loops.
True, but we still can't use it.
Yeah, we can. The way I stated the Cauchy principle of value theorem, or the Cauchy residue theorem, was that we had arbitrary curves.
No, well, I mean, we can use it for the entire curve, but
Yes.
for just the semicircle part.
Yeah, for that we've got a different, yeah, that's actually gonna be a slightly different argument.
Okay.
Where's the trouble spots? So let's go here. Let's start looking at this thing. Let's let r be big enough so that all the trouble spots are inside here. Where's the trouble spot for this integral? I. And where else? Where does this happen?
Negative r.
Yeah, right? So these are my two poles. I have two poles. Let's not talk about order yet, let's hold on. But one of them is up here, if r is bigger than 1, and the other's down here, and I don't really care about that one. This is the only pole that will be inside the curve we've created. So assume here that r is bigger than 1, because we're going to let r get unboundedly big. It doesn't matter if we make this assumption. It's totally cool. At some point, r will be big enough so that this is the picture. So we have this closed curve, and we're definitely moving in this direction, so we move in the right integration direction for the real axis. So this integral here, what did I call it? Gamma r over gamma r of that dude, c squared plus 1 cubed, is equal to 2 pi I times the residue of this function at I. If R is big enough, provided R is bigger than 1. So let's crank this out. So this looks weird, but it's all gonna be cool. Can we figure this out? What do you think the order of the pole is at I?
Third,
Yeah, why do you think that? That is right.
because 0 is cubed when you have I.
Yeah, exactly. So check this out. This bottom part is actually z minus I times z plus I. That's this cubed. So each of these factors is cubed. So it's really just 1 over z minus I cubed times z plus I cubed. Those are both poles of order 3. So nothing crazy going on here. This is awesome. So now I know the order of my pole. I have to know that before I proceed. And I can crank it out. Lots of ways we could do this. The easiest are the methods we talked about. So this is going to be 2 pi I times the limit as z goes to I of the what order derivative? Second order derivative. It's 1 less than the order of the pole. And I multiply by z minus I cubed times this original thing. Look at how cool that is already going to be. See how sweet? Had I not done that factorization, it would have looked a little different. Had you not caught this, at this stage, here's what you'd have. You'd have 2 pi I, or this is a slightly less wise computation. We would have this. We would still need to know the order of that pole, so in some ways the reasoning would have to be this. Oh, wait.
You miss, yeah.
I am missing something. Thank you.
Constant.
Yeah.
Well, also, aren't you missing a constant, like 1 over
Shit. Yes.
2?
1 over 2 factorial. Yeah, it's the order of the derivative. Thank you.
And isn't the c minus I to the third raised like squared again also?
No, that one's actually cubed, so that is actually the same depth
Oh, okay, yeah.
as the depth of the pole, because we want to
Yeah.
annihilate the pole. Does that make sense?
Yeah.
Yeah. So, yes, thank you. So then there's this 2 factorial out in front from this. I got that. And then your thing would look like this. Which is cool. It's just a lot more work. You can still do this. You'll just have to use the quotient rule twice. Yeah. So if you can see these algebraic factorizations and use them, it's going to make life easy. Hint, hint, yours will have a nice algebraic factorization. Pretty sure it's z squared plus 9, right, on your exam? It's a lot like this. So, just make sure this makes sense and let me know if it doesn't. But this would be painful. Ouch. So let's do this piece. Because look at how sweet it is. It was so sweet I accidentally forgot that piece. Those cancel. So nice. So this is 2 pi I over 2 factorial. Second derivative of z plus I to the negative third. And I'm going to do it like that because I'm a power rule guy. I have trouble thinking in the reverse of the upside down mode. So this is just gonna be pi I, and then first derivative, you get a -3 out in front. Second derivative, you're gonna get a -4 out in front. We've got z plus I to the -5th. So that's 2 derivatives right there in a row. And what we end up with, and sorry, I got the limit. I forgot the limit. So let's bring the limit back in. Limit as z goes to I of this thing. That means I'm just going to replace z with I. So let me do a little simplification here. I'm going to have 12 pi I over z plus I to the 5th. Do the plug and chug. And we've got 12 pi over 2I to the 5th. And that turns, that's 32I. So 12 pi I over 32I simplifies. And if at this point the i's don't cancel, something went wrong. Because this is going to be the value of our original integral, which is a real thing. There's no i's in it. So if you get here and you don't see these i's canceling, go back and figure out what happened. I'm not even going to simplify. Oh gosh, part of me just really wants to. So that's our final value, but I guess it's actually 3 pi over 8. So let me stop for a second, because I still have to address one piece. We didn't do this integral, right? We didn't do this integral, we did this integral. What is happening here that this top piece goes to 0? Ladies, can I help? Is there anything, what can I help you with?
I'm just, because I'm confused where the limit came from.
Because I forgot to carry it along, Grace. So
Okay.
thank you for carrying as always. So there should be a limit as z goes to I in there, and also here. Let's let you take a look at that. I don't care what trig we had to do. This beats the trig by a million times better. Trig substitution's a beast. So, why is this integral equal to this integral? So as r goes to infinity, equal to this thing right here. Why did that work? Why can we do this? And the answer is that the integral on just this top part dies out as r goes to infinity. So let's take a look at that. Let me show you how this works. I'm going to use a result. So let's select limit as r goes to infinity on just the CR part. So just that semicircle on top. I'm going to use the following result. And in fact, I'm going to slap absolute values on there. So use this result. That if I have an integral over some curve gamma of f of z dz, the absolute value of that is less than or equal to, we've used this once before, the length of gamma over the max value of f of z on gamma. The biggest the function can be here times that total distance across there. So let's do that here. So this is going to be less than or equal to the length, let's write it out, length of c sub r times the max of 1 over z squared plus 1 cubed on CR. So z is, sorry, I'll get out of the way. How long is this curve? It's a circle, perfect circle, perfect semicircle.
I pi r.
pi r. 2 pi r would be the full circle, so that's pi r. And now, this thing here, the max this is gonna be is, well, okay, well, I need one more result here. So I need this opposite of the triangle inequality. So also need this one that says something plus something else is greater than or equal to the difference of those two things. And I think I proved this a long, long time ago. I'm happy to prove it again if you don't believe that. It kind of comes from this. Let's say I have blah, and then I rewrite that as blah plus blah. And then I use the triangle inequality, which says that this, oh wait, minus blah, there we go. So I fake it out, I add in a 0 that looks like something. By the triangle inequality, this is less than or equal to that. Yeah, okay, it's cool. Plus that. Just shift that over to the other side so that this minus that dude there, the minus doesn't matter in the absolute value. So I've got 1/2 of it. If I now start with triangle and do this where it's triangle plus square minus square, then I get the reverse of this. I have triangle and square reversed, and so I can conclude that the absolute, doesn't matter what order, they're both less than or equal to this. So that's the result I want to use here. Now, why? Because the reciprocal of this is of importance to us. Notice how there's nothing in the top there. And to do something like this, I need to have something that's smaller down here than any possible value that I can have here, right? Because if I want this fraction to be bigger, the denominator has to be smaller. So, and actually this should say put absolute value on that, sorry. That should say absolute value on there. So what do I mean by that? That this, if I take the reciprocal, is less than or equal to, so see how I'm going to have reciprocal stuff? Less than or equal to 1 over, like so. So I'm going to use that here, and this is going to be less than or equal to the length of CR times the max of this thing, which is the max of, so I'm getting an upper bound on just this piece here. Z is on the curve. And I'm going to rewrite this as 1 over modulus of Z squared minus 1 cubed. So I brought the modulus inside here, I put the cubed outside. So I did this first. And then I used that inequality over there. This makes life good. Notice that the max, what is the max this can be? So what is the max of this thing on there, of this piece right here? What's the biggest this bottom can be? What's the biggest the modulus? What is the modulus? Actually,
The biggest
what
it can
is,
be is infinity.
it's, well, on this curve of radius r, what is the modulus of z? What is the modulus of every z on that top curve?
R.
R. So this is just literally equal to pi r, and then that modulus there is going to be 1 over r squared minus 1 cubed. And so now I've got this, pi r over r squared minus 1 cubed. What happens to that as r goes to infinity?
It goes to 0.
It goes to 0, right? I've got a first degree on top and a sixth degree on the bottom. This bottom blows up, and I've got that. So, my friends, I'm going to give you a cop-out for this. I'm going to help you out. Because I don't necessarily want you to do this whole thing again. I think we have a result in our book. Let me take a look. Some consequences of the residue theorem. Ooh, we might even have a sweet, sweet result you can just summon if you want. Let's see, so that would be. Yeah, they've got the thing I just proved in there, but I'm trying to find a nice result. Oh, shit. Okay, well, I don't see it here clearly. I'll send you a result you can cite. But what I want you to do is this process. I don't want you to do what I just did here about the top curve going to 0. Does that sound okay? Yeah, that makes it a lot. Grace looks really happy now. So I'll send you a result from the book that you can summon to actually do these two problems. So remember, to do these two problems, all you really have to do is find the residues. Where the hell was the original? Where was our beast? Our original beast was this. All you have to do is treat this like a complex integral over some curve that contains the singularity on the top half of the plane. Let's take a look at one of your other problems in there. So there's another one that I gave you that will be a little bit more work, but it's the same idea. It's problem 2C. So problem 2C looks like this. Your 2C is integral from negative infinity to infinity, x to the 4th dx over x to the 6th plus 1 dx. Let me get you started here. Same idea. We're going to think of this as first an integral on this semicircle, this part from r to minus r. As r goes to infinity, this will become our integral, and then we've got this upper part, where the integral will die as r goes to infinity. How many zeros does the bottom have? How many zeros are there to the bottom? 6. And we know how to find those because they are the 6 roots of -1. And they're going to be spaced evenly around the plane. So they're going to be in here somehow. 3 of them will be in the top half plane. Those are the 3 you care about. And eventually, when r is big enough, they'll all be in here. So this is going to equal the sum of the residues, sum of 3 residues. You just have to find those residues. That'll take a little work. There'll be some stuff to do here. Problem 3. Let me give you a tip on problem 3. Should you dare to venture into problem 3, and you should. It's fun. It's cool. This is the most interesting problem, I think, on the exam. We give you this. Now you can look up the answer. I think it's probably in the calc tables. So you can know if you did it right. But I'm actually asking you to develop the formula for this. Cut a Calc 1 student a break for once, why don't you? And give them a formula for cranking that out in terms of A. So you'll get some formula that depends on A, and it'll tell you what the value is for all A. That's kind of cool. But the way to do this is as follows. It's different than the way we just did it. Use a change of variables. So here theta runs from 0 to 2 pi. We're going to introduce complex variables. What a shock, right? Because every problem on this thing is complex analysis. So we're going to let z equal e to the I theta. This is our change of variables. We're moving from theta to z, but it's a little odd how we do it. What happens to z? What does z look like as theta runs its 0 to 2 pi? So unit circle?
It's the same thing at both points.
Yes. So you're talking about the endpoints?
So yeah, it's a closed loop.
It's a closed loop, absolutely. And it's a closed circle, right? Yeah, closed unit circle. Beautiful. So we're going to do this change of variables. Now all of a sudden, we're integrating around a circle of radius 1. We're letting z be this, but holy smokes, I don't see an e to the I theta. I don't see a z. What the hell? So here's what we're going to do. Let me get you a couple other pieces here. You need to express sine of theta in terms of z. So here's a cool fact. This should all make sense. Sine of theta is going to equal e to the I theta minus e to the negative I theta. Think about what's going to happen when you do this. The cos thetas will cancel, give you a 2i sine theta, so we put a 1 over 2i in front. So you can just use Euler's identity for this, and you can see that this is true. But we know that e to the I theta is something special. We just called it z. And this is 1 over z. So here's your substitution for sine of theta. Replace sine of theta with this expression. You're going to have it in there. You're going to have to simplify. You're going to have some division by 0 clearly introduced into the problem. So then we need to do the differential change. So let's take this and do the differential change. So dz is derivative of this side with respect to theta. But that's just z again. And so d theta gets replaced with dz over iz. So you need that, you need that. Yeah. This will actually affect the integral, and you need this. And your new problem will be do this integral of whatever that thing turns into when you make these substitutions.
Okay. But aren't you integrating over a different area?
Yeah, definitely. But it's the same. We're just doing a change of variables. As we lift away, as we lift from this, Noah, from this to this, we're also modifying everything else so that it maintains realness at the same time.
Okay.
Is that, do you know what I mean?
Yeah, I'll have to think on that.
No, that's cool. Yeah, it's good. Good. That's what I wanted. That's all I ever wanted. Well, it's been a pleasure, my friends. That's it for today. I'm going to be sitting in my office this time next week, waiting for y'all to come by. Be hanging out where people hang out. Come talk